The field of 3D reconstruction has been progressing really quickly in the past few years. Of course, with machine learning, artificial intelligence, with the advent of neural networks, things have expedited quite a lot. And 3D Gaussian splatting is one of those technologies which has come up fairly recently, but it has made such a big splash in the industry that everyone is almost looking into it, using it, and trying to incorporate it into their stack. All the big companies, be it Google's, Nvidia, Meta, you name the tech company, they are somehow utilizing this technology in their software stack, and they are actively researching on this and trying to create new products with this technology. So in this video, we're going to talk about Gaussian splatting in detail. I'm going to try to explain 3D Gaussian splatting in terms of a beginner, so that if you are very new to this field, this video can help you understand what Gaussian splatting is, and then go from there. You can read the paper going forth, or you can look at other research works, and hopefully you'd have some background understanding through this video, and you'd be able to better understand how 3D Gaussian splatting works. Welcome back to the channel, guys. My name is Dhruv. I am the engineer and CEO at Convolve. At Convolve, we assist small, medium, and large enterprises with their AI and computer vision needs. If you need any assistance, or if you want to get in touch with us, you can contact us. Here is our contact information. You can call us, email us, and we would be happy to assist you. We would be happy to talk to you. Now let's talk about today's topic, that is 3D Gaussian splatting. Now, why is Gaussian splatting such a big thing today in the field? Well, it offers amazing rendering quality, as we will see further in this video. Secondly, it is quick. Thirdly, not only does it offer good rendering, it offers a 3D reconstruction of the environment. So overall, to understand an environment in 3D, to understand how you can render novel views, how you can simulate an environment, there are numerous applications which this technology is able to really perform really well. We have done a previous video on nerves versus Gaussian splatting. So if you are wondering why do we need this, how is it better than nerves? Nerves were big revolution in their own field. Then why did we need 3D Gaussian splatting, or how it is better? You can watch that video. You can see the link on our channel. Now let's talk about 3D Gaussian splatting in detail. Now let's talk about Gaussian splatting in detail. So the 3D Gaussian splatting is a recent work. It just came out in SIGGRAPH of 2023, so fairly recent, about almost 10 months old. But in the field of computer vision and AI, even 10 months is like years, decades. So from that perspective, hopefully there's a lot of exciting stuff going on at the moment, and we will see something cool in CVPR this year. But regardless, came out in SIGGRAPH 2023, and it's out. The work is done by INRIA, University Côte d'Azur, and Max Planck Institute, and they have the paper, the code published, and the code is fairly well documented. In case you would like to see the code, or you'd like a video on the code, please comment in the video and we would go over it. So guys, what is so beautiful about this method? So this is a Gaussian splatting model you see on the screen, and this is trained model that is being used to render the scene from novel viewpoints. So these viewpoints may not have been seen in the training set. The camera is being moved around the scene, and the model has been trained from few images in the scene, and see how beautifully it reconstructs. And look at these balls, the spheres, the reflections on them are so real. We'll see why this is the case with Gaussian splatting. So before we begin, let's talk about what does Gaussian splatting entail, right? Let's take a step back and see exactly what is Gaussian splatting, or like what is the main building block of Gaussian splatting. So the main building block of a Gaussian splat algorithm is the Gaussians. Now, what are these Gaussians? You can think of it for simplicity just a point cloud. It's just a bunch of points in this 3D space that essentially have the structure of the 3D scene. So if you look at this particular image, you can see that this is essentially a point cloud. So think of Gaussians as these points in the 3D scene. In 1D, Gaussian is like a bell curve. In 2D, it's like a distribution, two-dimensional distribution. And in 3D, you can think of them as ellipsoids. These ellipsoids have different parameters like scale, rotation, spherical harmonics, and opacity. And let's talk about what these parameters means. So scale is essentially how big the Gaussian ball is, how big that ellipsoid is. Rotation is the rotation of that ellipsoid in the 3D space. So each of the Gaussians will have some rotation associated with them, and that will determine what orientation they have in the 3D space. Spherical harmonics. So this is the most important thing that defines the color. Spherical harmonics is a way of encoding the information about RGB color of a scene, and spherical harmonics have different orders: 0 order, 1st order, 2nd order, 3rd order, and each of those orders basically encode some information about the scene. The higher order spherical harmonics will encode information about higher frequency components of the scene, more about edges, and more about high frequency components such as leaves and stuff. And the low order spherical harmonics will basically have low frequency information, similar to what happened in NERFs with and without positional encoding. Here, high and low order spherical harmonics do that thing. And then opacity. Each Gaussian has an opacity associated with it, which basically defines whether there will be any light that will go through that Gaussian, or in other words, whether how powerful of a contribution that particular Gaussian will have on the final color of the image. Now, in an overview sense, the method works like this. First of all, you need to have a 3D point cloud of the environment to initialize your Gaussians. So that can be accomplished via structure for motion algorithms such as CoLMAP. You can initialize your scene through structure of motion. It will give you a bunch of point clouds, a bunch of points in the scene that roughly are according to the 3D environment, 3D construction of the scene, and that can be used to initialize the Gaussians. Once you have that initial set, then the next step is based on your camera viewpoint. You will try to use those initialized Gaussians to get a projection, get an image. So you will project those Gaussians and you will use a rasterizer to obtain an image. And now for that particular training camera view, you have obtained an image. And then the next step is that you will compare that image. So you'll compare this image with the image from this camera, and then you will compute a metric for error, and then you will do the back propagation to modify the parameters of the Gaussian. So the best part here is if you look at these parameters, these are defined for each Gaussian as just NN parameters. They are just tunable parameters. So it's not something too complicated. It's not even a neural network. It's just NN parameters. If you know torch, that's all it is. It's just a tunable weight parameter, nothing else. So once you've done the back propagation, now you are starting to learn the parameters of these Gaussians, that is scale, rotation, spherical harmonics, opacity, etc. Once you have basically learned, then over time you will improve your Gaussian parameters and get better and better at learning that scene. But before that process, let's understand how the rendering happens, right? So we talked about this rasterizer. So in NERF, if you remember, there used to be this camera, and then you will shoot out a ray of the camera, and then you will sample points along that ray to be able to get the RGB pixel for that particular ray. In Gaussian splatting, it's a little different. In Gaussian splatting, you have the camera and a bunch of Gaussians. There's no ray casting involved. It's a process called rasterization, which is a very common process in computer graphics. So essentially what happens is, based on the Gaussians in the scene, you sort them based on the depth. So from your camera, how far a Gaussian is, you sort them according to that, right? Of course, the Gaussians that are closer to the camera will have more impact than the Gaussians that are further away. That's why sorting is very important. After that, you just splat the Gaussians. So splatting is the process where you rasterize and essentially project them on to the camera to get your RGB. And while doing so, you do alpha blending, alpha composting, wherein based on the particular opacity of that particular Gaussian, you combine different Gaussians. So for example, if in this is your camera and there's these Gaussians in the scene, right? Based on their I've drawn really bad Gaussians, but essentially based on their you know, their power, their opacity and all that, you would weigh them, and then they will essentially play a role in the final RGB value. Here is how the algorithm looks like for you know, composting the different Gaussians together, which is very similar to how things happened in NERF. So this part is the same as your how the different volume density and your samples are concatenated together with the color, and then this part is equivalent to the transmittance calculation. So very similar to NERF, but just the concept is a little different. And then once you do the rendering with a trained model, this is the kind of output you get, which is pretty nice, right? Not only that, you have learned the 3D environment again, right? You started with an initial point cloud through structure from motion, but through this optimization process, that also becomes better. Gaussians are allowed to move around in the scene. And I think one important thing we didn't mention in the video, the Gaussians also have a position X, Y, Z along with rotation. So they're allowed to move around in the scene, and that way they are able to learn the 3D environment in a much better way. So that's it for this video, guys. I hope this video gave you some understanding about Gaussian splatting. 3D Gaussian splatting has had a lot of new work, a lot of exciting things come out after the initial 3DGS paper. So if you're interested, you should definitely go check out some of the work. It has been applied in autonomous driving. It has been applied in so many different applications, and it's really exciting. If you like this video, guys, please hit the like button, subscribe to the channel, and hit the bell icon so you are notified about any new video that we upload. I hope you like this video. Thanks a lot for watching, guys, and I'll see you in the next video.